Shallow friends, let's begin. Have you ever just stopped and wondered, how does medicine actually work? I mean, really, what's the magic behind it? Well, today, we're going to pull back the curtain and uncover that very mystery. We're diving deep into what happens once a drug gets inside our bodies.
Just think about it, yaar. You pop one tiny pill for a headache, and somehow it knows exactly where to go in this huge, complex body of yours and what to do. How? It's a fantastic question, isn't it? And I promise you, by the end of this session, you'll have the answer. So, the key to this whole mystery, it has a bit of a fancy name. It's called pharmacodynamics. Now, don't let that big word scaring off. It's actually quite simple. It's the field that gives us the complete picture of what a drug does in the body.
Okay, so what is it really? Simply put, pharmacodynamics is the study of what the drug does to the body, and, very importantly, how it does it. It's the full story you see, from the action of the drug to the effect you feel, the what and the how. That's it. Simple as that. Now, listen very carefully. This next point is probably the single most important rule in all of pharmacology. If you remember nothing else, remember this. I can almost guarantee you'll see it in your exams. And the rule is, drugs do not create new functions. They don't give our cells some kind of superpower. A heart cell can't suddenly start producing stomach acid just because of a drug. No way. Think of drugs like a volume knob or a speed controller. They can only turn up or turn down the processes that are already going on in the body. Okay, so if drugs are just these speed controllers, then what exactly can they do? What are the basic adjustments they can make? Well, it turns out there are 5 fundamental actions. Let's call them the 5 main moves in a drug's playbook. Let's break them down.
All right, let's go through them one by one. First up, you have stimulation. Pretty obvious, right? It enhances activity, kind of like how adrenaline gets your heart racing. The flip side is depression, which, diminishes activity. Think of barbiturates slowing down the brain. Then you have irritation. This one's a bit of a non-selective, noxious effect. Next is replacement. This is super straightforward. If your body is deficient in something like insulin and diabetes, we just replace it. Simple. And last but not least, cytotoxic action. Cyto means cell, toxic means poison. So it's about selectively killing invading cells. This is the whole principle behind antibiotics fighting bacteria or chemo fighting cancer.
So, we've covered the what. We know the 5 basic things drugs can do. But now for the really fascinating part, the how. How do they actually pull it off? You'll see that while a few drugs work in a very simple way, most of them are incredibly sophisticated. Okay, so there's a small group of drugs that work through really basic physics or chemistry. Think about antacids, for example. What do? They just neutralize stomach acid. It's a simple chemical reaction you probably learned in school. But, and this is a big but, these are the exceptions, not the rule. Here's the main takeaway, the real heart of the matter. The vast, vast majority of drugs we use today work by interacting with very specific targets inside the body. And these targets are proteins. This is what makes modern medicine so powerful and precise. It's not a shotgun approach, it's a sniper rifle. And this, my friends, is where the real magic of pharmacology begins. So if drugs are aiming for these protein targets, what are they? What do they look like? Well, it turns out that almost all drugs are designed to hit one of just 4 major types of protein targets. Just 4. Let's call them the big 4 of pharmacology. It simplifies things, doesn't it? And here we have it. This diagram, this is the master plan. The whole blueprint of pharmacodynamics is right here. Almost every single drug you will ever study acts on one of these 4 things: enzymes, channels, transporters, or receptors. Please, memorize this. Burn it into your brain. For today, we're going to focus on 2 of the big ones, enzymes, and then the most important of them all, receptors. All right, let's tackle the first target, enzymes. Now, have a look at this graph. I know, it looks a bit complicated at first glance, but trust me, it's actually very simple once you get the hang of it. All it's showing is how a drug can mess with an enzyme's work, either by inhibiting it or stimulating it, and basically changing the speed of a reaction. So a drug can block an enzyme in 2 main ways. Pay close attention, this is a classic exam question. First, there's competitive inhibition. The name says it all, right? The drug competes with a normal molecule, the substrate, for the exact same spot on the enzyme. It's like a race. Because of this competition, you need more substrate to get the job done, so the Km increases. But if you add enough substrate, you can still reach the maximum speed, so Vmax is unchanged. Then you have non-competitive inhibition.
Here, the drug doesn't fight for the same spot. It binds somewhere else, an adjacent site. And in doing so, it changes the enzyme's shape. It messes it up. So the maximum speed, the Vmax, goes down. But since there's no competition at the main site, the Km stays the same. Understand this difference? It's absolutely crucial. Okay, so we've talked about enzymes. And yes, channels and transporters are important too. But the big boss, the superstar of drug targets, is the receptor. By far, this is the largest and most important group. You could call them the master controllers of the cell. So what on earth is a receptor? Well, the best analogy, and it's a classic for a reason, is the lock and key. The receptor is the lock on the cell's door. The drug, or even a natural body chemical, is the key. When the right key fits into the lock and turns, the door opens and a signal is sent inside the cell. That's it. The receptor's only job is to recognize signals and pass the message along. It doesn't do anything else. It's a professional message receiver. All right, now that we know what the lock is, it's time to meet the different kinds of keys that can interact with it. Let's meet the main players in this game, the agonists and antagonists. This table here breaks it down beautifully. Let's stick with our lock and key analogy. An agonist is the perfect key. It fits, it turns, and it opens the door wide open. It produces the full effect. An antagonist is a faulty key. It fits in the lock, all right, but it doesn't turn. It just sits there, blocking any other key from getting in. It produces no effect on its own. A partial agonist is a key that kinda works. It fits and turns the lock, but only halfway. You get a little bit of an effect, but not the full one. And then there's the inverse agonist. This is a strange one. It not only fits, but actually turns the lock in the opposite direction, making it even more tightly shut than it was before. And this ability to turn the key after binding, we have a name for that. It's called intrinsic activity, and it's a super important concept to grasp. Now this diagram is just brilliant. It really helps visualize what's going on. It's called the two-state receptor model. The idea is that a receptor is not just sitting there waiting. It's constantly flipping back and forth between an active state, Ra, and an inactive state, Ri. So look at what happens. An agonist comes along and it prefers to bind to the active Ra state. By binding, it traps the receptor in that active form, shifting the whole balance and giving you a strong response. Now an antagonist, it has no preference. It binds to both the active and inactive states equally, so it doesn't change the balance at all. All it does is get in the way of the agonist. And the inverse agonist, it specifically seeks out and binds to the inactive Ri state, pulling the equilibrium in that direction, which is why you get an opposite effect. It's such an elegant way to explain it, isn't it? And really, that is the essence of it all. If you can properly understand these core principles, the four major targets, what a receptor is, and the crucial difference between an agonist and an antagonist, you have the key. This is the foundation for everything else. Master this, and you'll be able to figure out how almost any drug in the world works. So there you have it. We've gone through the fundamental principles, the major targets we know about today. But I want to leave you with a question to think about. We've mastered these four, but what else is in there? What undiscovered targets, what new locks are still hidden inside ourselves, just waiting to be found? Finding them could unlock the next generation of miracle drugs. And that, my friends, is the incredibly exciting future of pharmacology. Thank you. Namaste, everyone, and welcome. So let's get straight to it. We're going to tackle one of the most fundamental questions in all of medicine today. How does a drug, any drug, actually talk to a cell? This, my friends, is the heart of receptor pharmacology, and we're going to dive deep. Think about it for a second. How does that simple tablet you swallow for a headache know exactly where to go and what to do inside one tiny cell in your body? I mean, really think about it. It's not magic, yar. Not at all. It's actually a series of incredibly smart, super specific, you could say delivery systems or signaling pathways inside our cells. And today, we're going to decode them. Okay, so here's our game plan for today. We'll look at the G protein relay race, then the super fast ion channels, receptors that bring their own tools, and finally, the inside job of nuclear receptors. And then we'll tie it all together with dose and response. Stick with me, and by the end of this, I promise you'll have a paka, crystal clear understanding of all this. All right, first up, let's talk about the big one, the most common system in our body, the G protein-coupled receptors, or GPCRs. Now, the best way to think about this, imagine a relay race. A message gets passed from one runner to the next, and then to the next, until it finally crosses the finish line and causes an effect. That's a GPCR in a nutshell. So what exactly is a GPCR? Okay, imagine the cell membrane has a doorbell.
The drug comes along and rings the bell. But here's the thing. The doorbell itself doesn't open the door. No. Instead, ringing the bell alerts someone inside the house to go and do something. That's someone inside? That's our G protein. It's the intermediary, the first runner in our relay race, who takes the message from the door and runs with it. Okay, let's look at the first major pathway here, the CAMP pathway. Now, don't get intimidated by this diagram. It's actually very logical. Let's say a drug or a hormone, like adrenaline, binds to its beta receptor on the outside. This immediately wakes up a specific G protein on the inside called GS. Remember, S for stimulatory. This GS protein's job is to switch on an enzyme, which in turn starts making our very important second messenger, CAMP.
So here's that relay race, step by step. 1. Drug binds the receptor. 2. The GS protein gets activated. 3. This GS protein finds an enzyme called adenyl cyclase and turns it on. Now this enzyme, it's like a factory. It takes ATP and starts churning out thousands and thousands of CMP molecules. This is signal amplification. One drug molecule leads to thousands of CMPs. Then, step 5, CMP activates something called protein kinase A, or PKA. And finally, PKA is the guy who does the real work. It starts phosphorylating other proteins, which is basically like flipping a bunch of on switches inside the cell. And that gives us our final effect. For example, making the heart contract more forcefully.
Simple enough, right? It's a chain reaction. But what if the cell needs to send a totally different kind of message? Say, not making the heart beat faster, but constricting a blood vessel. Does it use the same CAMP pathway? Well, no. Nature is much more elegant than that. It has a different pathway, with a whole different team of runners for that job. And here is that alternate team. This time, a different G protein gets the call. It's called GQ. And GQ activates a different enzyme, phospholipase C. Now this is cool. This enzyme creates not one but two second messengers, IP3 and DAG. Now pay close attention to IP3. Its main job is to go to the cell's calcium storage and, boom, release it all. And let me tell you, releasing a flood of calcium inside a cell is like pulling the fire alarm. It's a very powerful, very urgent signal that triggers all sorts of things, like muscle contraction. Okay, everyone listen up. This table right here, this is a super high-yield table for your exams, so pay attention. It summarizes everything we just discussed. You can clearly see, for example, the beta receptors use the CAMP pathway, while alpha-1 receptors use the IP3/DAG pathway. You absolutely must know this. It's the key to understanding why different drugs do different things. Okay, we've talked about the GPCR relay race, which takes a few seconds, right? But what about things that need to happen instantly? I mean, right now. For that, the body has an express lane, and that express lane is called ligand-gated ion channels. So how are these different? Well, they're much, much simpler. Here, the receptor is the channel. They are one and the same thing. So when the drug, or ligand, binds to it, it's like a key fitting perfectly into a lock and turning. The gate just swings open, instantly. No G protein, no relay race, no second messengers, just direct, immediate access for ions to flow through. And because it's so direct, the response time is lightning fast. We're talking milliseconds, faster than the blink of an eye. This kind of speed is absolutely essential for things like nerve transmission, right? Where signals have to jump across a synapse almost instantaneously. This is the mechanism that makes that possible. All right, on to our third major category. I like to call these the receptors that bring their own tools to the job. These are the enzyme-linked receptors. Just imagine a mechanic who doesn't need a toolbox because the wrench is literally part of his arm. That's the idea here. And there are two main flavors of this. Have a look. On the left, you've got the receptor tyrosine kinase, or RTK. Here, the enzyme, the tool, is built right into the receptor itself. It's intrinsic. But on the right, you have the JK-STAT pathway. Here, the receptor is a bit lazy. It doesn't have its own enzyme. So when it gets activated, it has to call over a friend, a separate enzyme called JAK, to come and do the work. This table just makes that distinction crystal clear. RTKs have intrinsic enzyme activity. The receptor is the kinase. Think of insulin, that's a classic example. On the other hand, JAK-STAT receptors recruit a kinase. The receptor is just a docking station for the real worker. This is how things like cytokines and growth hormone work. It seems like a small difference, but functionally it's very, very important. Okay, now for our fourth and final mechanism. And in many ways, this is the most profound of them all. I call this one the inside job.
See, so far, everything we've talked about, the receptor was on the cell's surface, like a doorbell. But here, the drug doesn't just ring the bell. It breaks in, goes all the way inside the cell, and heads straight for the control center, the nucleus. Now, this is by far the slowest mechanism. We're not talking seconds or milliseconds anymore. We're talking hours for an effect to show. And you have to ask, why so slow? Well, it's because this mechanism isn't just flipping a switch on or off. It's literally going into the nucleus and rewriting the cell's instruction manual, the DNA. The effects are so profound and long-lasting because the drug is changing the very proteins that the cell produces.
Let's trace the journey on this diagram. First, the drug has to be lipid-soluble, like a steroid, so it can just slip right through the cell membrane. No need for a door. Once inside, it finds its receptor, which is just waiting in the cytoplasm. They pair up, and this new drug receptor complex travels together into the nucleus. And there, it binds directly to the DNA and starts changing which genes are being read. It's directly altering gene transcription.
So, let's just quickly summarize the key points here. 1. These work for lipid-soluble drugs. 2. The receptor is inside the cell, not on the surface. 3. They work by directly altering gene expression. And 4. This all leads to a very slow onset of action, but the effects are incredibly long-lasting. The perfect example is corticosteroids, right? You take them, you don't feel anything for hours, but then the effect stays for a very, very long time. Okay, fantastic. So we've covered the 4 main ways drugs talk to cells. That's the how. But now for the most important part, the so what. How does all this basic science connect back to our patients, to the clinic? How do we use this to decide on doses and predict a drug's effect? This is the clinical payoff, everyone. This graph you see here, this is probably the single most important graph in all of pharmacology. It's the dose-response curve, or DRC, and it's really simple. On the bottom, you have the dose of the drug, and on the side, you have the response. As you increase the dose, the response goes up. But then notice how it flattens out. It hits a plateau. That ceiling means that giving more drug won't give you any more effect, probably because all the receptors are already occupied. And you'll notice we plot the dose on a log scale. That just helps stretch out the curve into this nice S shape, which makes comparing drugs much easier. All right, another very, very high yield point. You must understand the difference between these 2 words, potency and efficacy. They are not the same thing. Potency is all about the amount of drug needed. How much do you need to get an effect? A more potent drug is simply one that works at a lower dose. That's it. Efficacy, on the other hand, is about the maximum effect a drug can produce. How high can that response go? It's the height of that plateau on the curve. They are 2 completely different concepts. Let's make this practical by looking at this graph. See drug D, its curve is the furthest to the left. That means it needs the lowest dose to work, so drug D is the most potent. Now, look at drugs A and B. See how their curves go higher than everyone else's? They produce the biggest response, so drugs A and B have the highest efficacy. And here is the main takeaway. Please write this down. More potent does not mean better. If you have a patient with severe pain, do you want a potent drug or a high-efficacy drug? You want the one with high efficacy, the one that can actually stop the pain. So I'll leave you with a clinical question to think about. A patient has been on a drug for years, and it's been working perfectly. Then, one day, it just stops working. The patient says they aren't getting any relief. So what's happened? Is the drug bad? Or has the cell itself adapted to the drug by changing its receptors? Think about that. This question leads us right into the fascinating topics of tolerance and receptor desensitization. But that's a story for our next class.
Thank you very much.
Hello bachon and welcome. Today we are going to dive deep into something really fascinating, pharmacodynamics. We're going to uncover the secret life of drugs. What are they actually doing inside our bodies once we take them? Chalo, let's get started.
So let's begin with a question that you, as future doctors, will face every single day of your career. How do you choose not just any drug, but the best and the safest drug for your patient? This question is the very heart of everything we're going to talk about today.
To answer that, you first need a way to evaluate a drug, right? So think of it like this. Like a drug has its own report card. We have certain criteria we use to judge its performance, to see if it's an A+ student or not so much. First on this report card is something called selectivity. A selective drug, it's like a sniper. It hits exactly the target it's supposed to, giving us the effect we want without causing a lot of collateral damage, what we call side effects. A smarter drug just knows its job and sticks to it. Now, have a look at this slide. It shows selectivity so clearly. See the red curves A and D? That's for salbutamol. Curve A is the good effect, opening the airways. Curve D is the side effect, making the heart race. See that huge gap between them? That is excellent. Now look at the blue curves for isoprenaline. They are so close to each other. This tells you immediately salbutamol is way more selective, and because of that, a much safer choice.
This idea of a safety gap, it leads us right into our next really important concept, something critical for patient safety, the therapeutic range. You'll often hear it called the therapeutic window. It's basically the sweet spot for any drug's dosage. And this picture shows that window perfectly. The blue curve, that's the drug working, giving the therapeutic effect. The brown curve is the adverse or bad effect. The therapeutic range is that dosage zone where you're getting enough of the blue curve's benefit without getting too much of the brown curve's harm. Our entire job as clinicians is to keep our patient's drug level right inside this safe and effective zone.
Okay, so we've talked about how a single drug performs, but things get more interesting. What happens when we give a second drug at the same time? Are they going to be friends and help each other out? Or are they going to be foes and start a fight? Let's find out if it's teamwork or a tussle.
Really, it boils down to two main possibilities. On one hand, you have synergism. This is when the drugs give each other a helping hand. Their combined effect is actually greater than what either could do alone. On the other hand, you have antagonism. This is a tug of war. One drug actively reduces or sometimes even completely stops the effect of the other.
Now, within synergism, there's a very special kind of teamwork called potentiation. And this is so interesting. This is when you have one drug that, by itself, does absolutely nothing. But when you give it with another drug, it acts like a super booster, making that active drug much, much more powerful. This graph shows it perfectly. See the red curve? That's drug A working by itself. Now, drug C alone, it does nothing. It's just a flat line. But look what happens when you combine them. The blue curve, C plus A, is shifted way over to the left. This means you need a much smaller dose of drug A to get the very same effect. Drug C has potentiated drug A. It's quite amazing.
All right, Butcho, now for the main event. Let's get into the most common type of drug fight you will ever see. This is the heart and soul of pharmacology, the epic battle that happens at the cellular level, the battle for the receptors. This slide shows the two main fighting styles. Let's look at the left first. This is competitive antagonism. In diagram D, you can see the antagonist drug and the agonist, the good drug, are fighting for the exact same spot. The antagonist is basically just blocking the parking space. Now look to the right, diagram E. This is non-competitive antagonism. Here, the antagonist binds to a totally different spot, but by doing that, it changes the shape of the whole receptor. It's like a jam the lock, so now the key, our agonist, just doesn't fit anymore.
And here are the results of that battle, shown on our dose-response curves. Check out the graph on the left. With a competitive antagonist, the curve just shifts to the right. This means the block is surmountable. If you just add more and more of the agonist, you can eventually win the fight and still reach that 100% maximum response. Now look at the graph on the right. With a non-competitive antagonist, the curve is flattened. The maximum response is suppressed. It doesn't matter how much agonist you add, you can never reach the top. That block is insurmountable. So, this table summarizes the crucial points for you. Competitive, same site, parallel rightward shift, surmountable. Non-competitive, different site, curve flattens, insurmountable. And the analogy says it all, really. Competitive antagonism is like fighting for the same chair. Non-competitive is when someone just comes and breaks the chair so nobody can use it. Okay, so why have we learned all this? Why does any of this matter to you as a future doctor? Let's bring it all back to the clinic, back to the art of writing a prescription.
Understanding these tiny, invisible battles and alliances happening inside the body, it's everything. It's what allows you to predict drug interactions, to reverse a drug overdose using an antagonist, and to combine drugs to get a better effect with fewer side effects. This isn't just theory for your exams, Bacho. This is the science of keeping your patients safe.
So I'll leave you with this final thought. The next time you or anyone in your family takes a medicine, just think about this. What invisible, microscopic battles and alliances are happening inside? It is a complex, elegant, and powerful world at work, all to help us heal. Ponder that.